Hi, this is Hobbyman5000, and today I'm going to describe the initial steps about creating your this search-based AI that I'm working on. The link to the bitbucket is down below. It's a Git repo, and you can check it out. Anyway, the game it's based off of, or the game it's working for, is called Faerie Alchemy. So way back 4 years ago or so, when I was searching for the job I am now leaving, I was building all sorts of programs as an online portfolio. And so part of that is coming up with ideas for things. So I was playing this game, and in sort of between programming projects, and I was frustrated that I couldn't see the last piece. I kept dying in the 300,000 to 400,000 range, and I just could not earn that last piece or whatever. And so what I ended up deciding is that in Ruby, to practice the language, I was going to write this AI. Well, I ended up getting hired before I could get much farther than playing the game in ASCII text. So I ended up scrapping that whole thing and just continuing on with work. Well, now I've kind of, given the name of the channel, I've got enough hobbies going on that I haven't been hobby programming for a very long time. And so now it's come down to that I need to rebuild this online profile. And so that's why I'm coming back to Python to start putting things online for that, so people know that, hey, I can actually program in this language. So this is an AI for that game, for that purpose. So that game is basically a mix between Tetris and Bejeweled. I have a link to the Congregate version down below. A note about it, it has a bug in it. The first game you play is actually harder than the rest of the games you play, unless you clear your cookies and refresh or that kind of thing. And that's because the first game, you have to earn each piece by actually building that piece. But in the games after it, which are actually the way the game's intended to be played, are a little bit easier because every time you pass a point threshold equal to the piece that you're trying to earn, you earn the piece. So my AI, because of the issue with that dichotomy, even though I could program both, I'm going to have it focus on playing the harder version first and see if I can get it to be better than players on this harder version. And then if I can't, maybe I'll worry about abusing that fact later on. But you can always play both versions with a couple of minor tweaks, and yeah. So the idea of the search-based AI is this is the same way that chess AIs work for the most part, is that they search a whole bunch of moves in advance and figure out objectively, if you're playing this shorter version of the game, i.e., how do I win in the next 5 moves, so to speak, where winning is some abstract idea of points that the programmer has given all these values. They will try and win this 5-turn game, or this 10-turn game, or whatever. And it's actually the AI playing against itself as it tries to eliminate every possibility. And basically, that's how it works. It's not actually all that interesting when you think about, okay, well, you're just scoring pieces and then counting up to see which board states are better. Most of what search-based AI is finding ways of eliminating huge amounts of that search early, so that you don't search down paths that are pointless. And so that's what you're going to be seeing in upcoming videos as I actually develop the AI. Where I'm currently at is just the game works, the rules are there, and you can look at it in ASCII text. And there's an AI there that plays with random moves. And this kind of verifies that the game is working, that it can deliver its moves out, and I can load board states and all of these things, allowing the AI to actually play the game. So, and in a search-based AI, if you're going to be searching all those moves, you have to have all of that game kind of programmed in, so it's not playing its own version of the game, right? So, the plan before I talk about branching factors and close out the video is to first build this game up. So that's done. The next part is to build the AI and continue adding steps and figure out which steps actually help the game versus hinder the game, and how high I can really get it scoring before I have to find new ideas. And so then, after I get the AI to a suitable point, the hope is that it's scoring high enough that I can start making it top charts. And then that kind of proves that the AI works real well. if it's beating people out, that's good. So the next bit is to I actually want it to then go online and play the game for me, and indeed actually get on those top charts. And so that's actually going to be its own web app. So first you have the game, then you have the AI, and then you have the little manager over here that actually hooks up the two and whatever. And then eventually you're going to have a third module that goes up and opens up Chrome, and with no incognito, so there's no cookies or whatever, and then it'll play the game and refresh so it doesn't play the second version of the game unless I decide that I want it to do that, and it'll actually go and start playing the game over and over and over until it fill up the top scores or whatever, and it'll be doing this all legally, and so lots of work to do. So anyway, the first thing I want to talk about today, I guess I'll start and show you that the program actually works just to humor you here. So we're gonna run main, and it played a bunch of moves, and it got a score of 255, or 258, I guess, and it died because these are just random moves that it's making. That's odd. Okay, good. Okay. Thought I saw a bug, but it was working just fine. Alright, so anyway, you can tell that the score isn't that good. This is something, you're making random moves, so this is putting no thought into it. It's just literally just hitting some random number of keys and then dropping the pieces in and seeing what happens, and oops, I died, right? So this is like a 4-year-old playing the game who doesn't understand the game. They're just boo. So anyway, and that's pretty typical for what I've been getting with my experiments. It's between 250 and about 1,000 points, maybe on the top end, if it got really lucky. And anyway, so that's a good baseline. If I add AI and a little bit of searching, it should do way better than that. So, anywho, let's get to the actual, what was I talking about? Branching factors. So I got a notes thing here that talks about branching factors, so I'm going to bring that up. So you have 5 spots that you can drop pieces from on top. You have, horizontally that is, and then you have 6 ways that you can drop them vertically. And then you can invert the pieces and do the other 5 and the other 6, right? So that's 22 moves unless the pieces match, in which case it's 11. I'm going to talk about why I don't care too much about the matching anyway later on in a different video. But so for now, assume the worst case, which is 22, at least for known pieces. So the first 2 moves that you see is a branching factor of 22 for the first move and 22 for the second move. This gives you a 484. The rest of the times I talk about this, I'm going to try and call it 500, but it's actually 484 different moves that it's going to play, and that's super fast. It's going to do that, in less than thousandths of a second, right? And so we're always going to search those 500 because it gives us a maximum amount of information. And what we're going to do from there is try and prune off trees of further moves, so that previous 484 branching factor isn't brought back down to a reasonable, or 484 different moves that we've done is brought back down to something more reasonable, like 10 or 5 or 15 or something, right? So that way, when we get to the next branching factor, which is horrendous, we can get an extra move or 2 down that way. So the next branching factor is, unfortunately, the number of types of pieces you have in every combination, and then multiplied it by 22, unless they match. That ends up being pretty huge. That means even with just the 2 pieces, you have 3 different ways that you can get those, and so you end up getting something like a branching factor of 55 or 68, or I don't quite remember now, because I didn't do the math in the last week. It was a while ago. But here you go. I have the function if you really wanted to go calculate it, but it gets really bad. By the time you get up to 10 piece types, you're talking a branching factor of 1100. That means to search 2 moves, you're already going past 1,000,000. So we have to trim that way down. And that, mind you, that's 1,000,000 that would be times your 484. And 484 million, I don't know how many board states I'll be able to search before I run out of time. I'm only going to give it a 3 or 4 second window at most. That way it kind of feels like a human's playing and that kind of thing. So I don't know if I'll get to billions or not. We're going to have to experiment. I'm not super familiar with how fast Python is. I'm normally a C++ type of guy. So if I really wanted this to be mega fast, I'd probably go to C++ and spend all sorts of time optimizing the way it thinks about things. But really what I'm trying to do is build it up in a language that I'm not used to, as a way to kind of learn the language and get it to feel out. So, what we'll be getting to in the next video is heuristics and a few ways that we can, the first pruning that I'll be doing to get that branching factor way down, at least early on. That way, as the game goes on, we can continue searching 4 or 5 moves deep and hopefully beat out the ability of human players to outthink the computer. So I will see you then, and that video will come out basically as soon as I get the next piece or 2 of this AI in place, so it's actually an AI and not just a thing that spits out actually random moves. And hopefully it's getting a reasonable score by that point. So I will see you guys later. Bye.